Hello everyone, I'm today's presenter Jiayu Su. I'm from NCTU Taiwan and my advisor is Katia Fang. Today's topic is effective capacity maximization for multi-technology-based 5G NR networks. This is our today's outline. We'll have a brief introduction and then interview the system model and problem formulation. Later on, we'll propose the algorithm to solve the formulated problem. Lastly, performance evaluation and conclusion will be mentioned. Here comes the introduction part. As various wireless services proliferate in the future mobile networks, the 5G new radio access technology is expected to fulfill three service classes, including eMBB, MMTC, and URLLC. These services are associated with different set of user equipment requirements, which are changing for the system with current OFDM transmission to satisfy. To realize such diverse service requirements, 3GPP introduced advanced OFDM-based waveform and multi-numerology. The term numerology refers to a set of parameters such as subcarrier spacing or symbol duration, which a multi-numerology network has gained significant attention owing to its potential to facilitate achievement of the efficient 5G NR networks. Concretely, the module with larger symbol duration can be chosen for MMTC to support delay tolerance application, while smaller symbol duration is more suitable for URLLC to satisfy stringent delay requirement. To overcome overhead in multi-module network, reference 3 proposes a heuristic method to find efficient number of numerologies. With fixed number of numerology, reference 4 design package scheduling algorithm with consideration of fairness among user equipment, and reference 5 further develop scheduling algorithm under flexible numerologies in both frequency and time domain. However, reference 3 to reference 4 and reference 5 only adopt equal power allocation scheme, which may cause inefficient use of power resource. Moreover, existence of multi-module with different subcarrier spacing will destroy the orthogonality of a multi-carrier system and induce additional inter-module interference. Based on water filling criteria, in order to maximize total throughput of the considered multi-module networks, more power should be allocated to channels with higher gain. Nevertheless, the newly produced in multi-module networks will have different interference patterns in OFDM systems, and therefore conventional power allocation method needs to be redesigned. On the other hand, performance of evaluation of multi-module network in current literature are based on shipment capacity, while it is recognized as a suitable metric for systems with delay-insensitive application. Thus, it is not feasible for multi-module networks. By comparison, effective capacity, which can be interpreted as maximum arrival rate, is able to provide more comprehensive performance evaluations by taking both achievable capacity and delay requirement into account. Motivated by aforementioned research, this paper studies first power allocation problem for multi-module based on 5G new radio networks. Original optimization problem aims to maximize total effective capacity under transmission power constraint with consideration of inter-technology interference. A geometric programming-based power allocation (GPA) scheme is proposed to cope with the non-convexity caused by inter-technology interference. Lagrange dual method is applied to search for power allocation decisions. Simulation results demonstrate impacts of inter-technology interference on power allocation result, and show that the proposed GPA method outperforms others baseline. Now we are going to system model and problem formulation section. In this paper, we consider downlink transmission of a single-cell multi-module networks with provision of k different services. Besides, each service has distinctive number of subcarrier and subcarrier spacing to serve user equipment and provide various QoS. Number of subcarrier and subcarrier spacing of K surface are respectively denoted as Nk and delta Fk. Simple duration of K surface can be expressed as this equation. It can be seen as larger subcarrier spacing delta Fk is accompanied with shorter simple duration Tk, and vice versa. Moreover, the equivalent Q model of the considered network is figure 2. As we can see in the figure 2, service data will initially enter into a first-in first-out buffer as a constant arrival rate and transmit to a corresponding user equivalent over a wireless channel. And here, RKW represents spectral service rate from the W subcarrier and the K service, and it can be written as equation 1, where PKW is allocated power for the W subcarrier of K service. H is channel vector between W subcarrier of K service and the corresponding UE. IKW is inter-branch interference and can be expressed as equation 2, where JKW is spectral Dirac vector. It can be modeled as summation of exponential function or sinc function. For detailed formulation of JKW, readers can refer to reference 9 equation 18 and reference 10 equation 10. Sigma squared is noise power density. With spectral surface rate in equation 1, the effective capacity can be expressed as the following equation, where θk is delay exponent, indicating whether delay requirement is stringent or loose. Note that equation 3 can be interpreted as maximum arrival rate μkW that can be supported by spectral surface rate from W subcarrier and K surface, subject to the delay exponent θk. EH indicates expectation operator with respect to channel vector H. The optimization problem aims to maximize the total effective capacity under transmission power constraint, can be formulated as follows. Here P is a symbolic notation representing power allocation. Note that problem 4 is challenging to solve since the objective function for A is not convex. By applying convex optimization techniques of proposed GPA algorithm, problem 4 can be transformed into a standard concave maximization problem. Now we are going to propose a geometric programming-based power allocation GPA algorithm to solve the aforementioned problem. In our proposed GPA algorithm, we firstly tackle the non-convexity of the objective function by estimating its lower bound and variable transformation, and the optimal power solution will then be obtained by the Lagrange dual method. To convert the objective function into a concave function, a lower bound equation is used and given as follows. By using inequality from equation 5 and variable transformation, the original problem can be written as follows. Since log sum exponential and expectation function are convex and linear functions respectively, 6a will be a concave function, and thus the optimization problem 6 can be solved by the Lagrange dual method. Lagrange dual function can be expressed as equation 9, where lambda is Lagrange multiplier, and therefore the dual problem for equation 9 can be written as follows. The solution for ultra problem of 10 can be obtained by applying the equation of gradient descent method for fixed p, and is given as equation 11, where s and epsilon are iteration index and step sets respectively. And the plus superscript is identical to take a maximization function with 0. On the other hand, dual function can be expressed as the following equation. By setting equation 12 equal to 0. The power allocation solution of P is given as follows. The proposed GPA algorithm is then summarized in algorithm 1. In GPA algorithm, first will initialization the parameters, and after initialization, draw variable lambda is updated with equation 11 based on fixed P, and P will be determined with equation 14 under a given lambda. The above process will be repeated iteratively until the proposed scheme converges. Now we are going through the performance evaluation section. In our simulation, there are two circuits with number of subcarriers equals to 10, and subcarrier spacing delta type 1 equals to 30 kHz and delta type 2 equals to 15 kHz. Subcarriers with index from 1 to 10 belongs to service 1, whereas index from 11 to 20 are associated with service 2. H is simulated as ready fading in each fading block. The key system parameters are mainly referred from reference to and listed in the following table. Moreover, random power allocation and equal power allocation are additionally implemented as baseline schemes for the purpose of performance comparison. Figure 3 studies INI power. It can be seen that subcarrier closer to unshaded margin will suffer from larger INI power. Moreover, it can also be observed that INI power of service 2 is periodically equal to 0. This phenomenon occurs whenever subcarrier spacing of service 2 fall onto a multiple of subcarrier spacing of service 1, which is consistent with the analysis of INI power in reference 9 and reference 10. Figure 4 investigates allocated power to each subcarrier by proposed GPA and EPA scheme. It can be seen that subcarrier if experienced from larger INI power will be allocated less power and vice versa, which is similar with water filling principle. Figure 5 displays total effective capacity versus subcarrier index to investigate performance of each subcarrier. This can be seen that total effective capacity of each subcarrier has similar pattern with figure 4, which implies that larger INI power will result in lower achievable effective capacity. Consequently, the necessity of power allocation design to alleviate performance degradation from INI is suggested in figure 5. The superiority of proposed GPA algorithm is shown in figure 6. It can be observed that the proposed GPA method is able to achieve higher total effective capacity than EPA and RPA scheme. The impact of ratio load on INI power is investigated in figure 7 and 8. In figure 7, it can be seen that INI power of all subcarriers is 0 when load equals to 1, as subcarriers between different surfaces are orthogonal to each other. Moreover, since INI power of surface with smaller subcarrier spacing will be periodically equal to 0. As mentioned in figure 3, this can be observed from subcarriers 11 to 20 that the number of subcarriers that have non-zero INI power is inversely proportional to the subcarrier spacing ratio. Furthermore, by the fact that the number of subcarriers with non-zero INI is increasing when load becomes larger, the INI power is proportional to subcarrier spacing ratio low as shown in the figure 8. Finally, we'll have the conclusion. This paper proposed the GPA algorithm for power allocation problem in the limited margin networks. Now, complex objective function resulting from INI has been converted into a concave function from the proposed GPA scheme. Power allocation solution was then searched by Lagrange dual method. Simulation results disclose the effect of INI on power allocation results and illustrated the superiority of our proposed GPA method. Here are the references. Thanks for watching this video.